Think about the animals humans actually eat: cattle, deer, goats, rabbits, fish, chickens. Nearly all of them are herbivores or grazers, animals that eat plants. Now think about how often anyone eats a lion, a wolf, an eagle, or any other predator. Almost never. And that's not some recent food trend or squeamish modern preference. That pattern holds across nearly every traditional human culture, in nearly every corner of the world, for about as far back as anyone can trace it. And it turns out there are real solid biological reasons behind it, not just taste. The first reason comes down to simple energy accounting, and a researcher named Raymond Lindeman worked out the math behind it back in 1942. Lindeman studied how energy actually moves through a food chain, from the sun into plants, from plants into the animals that eat them, and then into whatever eats those animals. His finding, now often called the 10% law, is that only about 10% of the usable energy at any one step in that chain makes it through to the next step. The other 90% gets burned off just keeping that animal alive, its heartbeat, its body heat, all the ordinary business of being a living creature. So a plant-eating animal is sitting one step away from the sun's original energy. A predator that eats that plant-eating animal is sitting 2 steps away and has already lost a huge amount of usable energy along the way. Hunt a deer, and you're tapping into a comparatively rich energy source. Hunt the wolf that hunts the deer, and you're going through an enormous amount of effort and risk to get a far smaller energy payoff, because so much of that energy was already spent before it ever reached the wolf's body at all. Picture it as a rough chain. The sun feeds the grass feeds the deer, and the deer feeds the wolf, with roughly 90% of the usable energy disappearing at each single handoff. By the time energy reaches a predator's muscle tissue, it has already been taxed twice over, once turning sunlight into plant matter, and once turning plant eater into predator. A pound of wolf meat, in other words, represents a far larger slice of the ecosystem's total energy budget than a pound of deer meat does. For a hunter who has to invest real time and real risk either way. In pure survival terms, chasing predator meat is often just a bad trade, spending more effort to chase down comparatively little payoff, when an easier, more energy-dense meal was usually just one trophic level away. The second reason has to do with what a predator's body tends to be carrying, beyond just calories. A team of researchers, Jennifer Malmberg, Lauren White, and Sue Van de Wood, published a study in 2021 looking specifically at how parasites and pathogens move through a food chain, and found that they concentrate as they climb it, in much the same way energy gets lost climbing it. Every parasite or disease living in a plant eater's body has a chance to pass into whatever eats that plant eater, and then again into whatever eats that. By the time you reach a top predator, an animal that has spent its whole life killing, handling, and eating other animals, its body has had far more opportunities to pick up dangerous hitchhikers than a grazing herbivores ever did. Eating predator meat isn't just a worse energy deal. It's frequently a much riskier one, biologically speaking, loaded with a heavier, more concentrated dose of whatever parasites and pathogens happen to be circulating through that entire local food chain. This is a version of a broader pattern ecologists call biomagnification, usually discussed in the context of environmental toxins building up as they move up a food chain. But Malmberg, White, and Van de Vood's research showed the exact same climbing concentration effect applies to disease exposure too. A grazing animal mostly just has to deal with whatever it happens to pick up from plants, water, and soil. A predator has to deal with all of that, plus everything every single prey animal it has ever eaten was already carrying, stacked on top of each other, generation after generation of exposure compounding upward through the food chain. And then there's a third danger, specific enough that it has a real, documented, and genuinely tragic case behind it. In 1912, an Antarctic expedition led by Douglas Mawson set out on a long mapping journey with 2 companions and a team of sled dogs. Far from their base camp, an accident with a crevasse claimed one team member, along with the sledge carrying most of their food and nearly all the dog food. With hundreds of miles of frozen, hostile terrain still between them and safety, Mawson and his remaining companion, Xavier Mertz, made the difficult decision to survive on what was left: their own sled dogs eating the meat, and critically, the livers, since almost nothing else was left to eat. Mertz grew increasingly ill over the following days, eventually dying before the party could make it back to safety, while Mawson suffered severe symptoms of his own but survived. Decades later, researchers John Cleland and Ronald Southcott proposed an explanation: hypervitaminosis A, a toxic overdose of vitamin A, a nutrient that predator livers store in extremely concentrated amounts, since a carnivore's own diet is already so vitamin A rich to begin with, and the liver is exactly where a body warehouses that surplus for later use. A herbivore's liver simply never accumulates anywhere near that concentration because it was never processing that much vitamin A in the first place. It's worth being clear that the exact cause of Mertz's death has never been settled beyond doubt, and cold, exhaustion, and general malnutrition were almost certainly factors too. But the vitamin A theory remains one of the most widely cited explanations, and it points at something specific and real. The liver of a predator can concentrate a nutrient to a level that's actively poisonous to the animal that eats it next, a danger largely absent from herbivore meat. Put those three things together, and you get three separate independent reasons: an energy problem, a parasite problem, and in some cases a genuine toxicity problem, all quietly pointing the same direction. None of these reasons required any ancient human to understand trophic levels or hypervitaminosis A by name. Nobody needed a research paper to know that hunting a predator was exhausting and dangerous for comparatively little meat, or that eating a top predator's flesh seemed to make people sick more often than eating a deer's did. Across countless generations, in wildly different environments around the world, the lesson arrived at the same conclusion again and again, the hard way, through direct experience, and then simply got passed down as a habit that felt obvious, one nobody needed to write a rule for. Cultures thousands of miles apart, with no contact with each other at all, ended up building their diets around the same basic pattern, not because they compared notes, but because the same underlying biology was quietly teaching everyone the identical lesson. So, the next time you notice you've never actually eaten a lion steak or a wolf chop, and it's never even occurred to you to ask why, that instinct isn't random. It's a genuinely old piece of accumulated human knowledge, worked out through generations of trial, error, and occasionally, as in Mertz's case, tragedy, long before anyone could explain the biology behind exactly why it was true. Three completely different scientific fields: energy ecology, disease ecology, and basic nutritional toxicology, all independently converge on the exact same practical rule of thumb your ancestors seem to have already been quietly living by. Not a coincidence, and not a taboo invented for no reason. Just biology, discovered the hard way, long before anyone had a name for any of it.